we are going to teach one concept about the Faraday law, Lenz's law, and electric field in the brain. So then we will be just handing over as the lesson will be going on. Thank you. Are you ready? Yes. Okay, I think to start with a very interesting question in electrodynamics, which says that how can we generate electricity without a battery? Okay? How can we generate electricity without a battery? So you have to be attentive that I can ask you randomly to answer the question, okay? But we are going to make it smooth. Just take time with the background you did in electromagnetism, module. Just how can you answer this question? How can we generate electricity without a battery? Okay, who has an idea? Suggestion, please. How can we get electricity without having a battery? Imagine that you want, for example, writing, but you don't have a battery. How can we generate it? As a good student who studied electromagnetism model. Okay, thank you, Justin.
Thank you. I think you can generate electricity by using magnet and coil, as you have studied in electromagnetics.
Wow. How can we award him? Clap for him. Okay, thank you. That's indeed great. So, we are going also to see the demonstrations.
Okay, thank you. I think you can generate electricity without battery by using magnet and coil.
Okay, so how can we award him? Wow, wonderful. So, as we are going to proceed, we are going to see the demonstration. Okay? So, imagine that as he said, we need a bar magnet. Let's say that here there is north and here there is north. Okay? So then let's say that we have here coiled wire. Okay? Are you seeing here? So coiled wire. Then here, let's say that is the magnetic field lines. Okay? So because here there is north and here there is north, they will be coming out. Okay? So then remember this is a coil. Okay? So if we move, if we pull this bar magnet to close over this coil, okay? Yes. What we'll be getting that there will be inducing of current. That is how we started. So how we be going? We be going clockwise. Current will be going clockwise in the coil. How are we going? Just to name the direction, clockwise. How does it go in? The clockwise is like this. Okay? Yes. It means that if I turn like this, I'm not changing the direction. You see that? Yes. Just I'm flipping from not having this XY plane, then turn to this plane. Okay? It means we'll be going like that. Like that. It is also the similar in clockwise. So it will be moving like this. Every person is understanding why clockwise is I put this direction to be like that, instead of opposing it to be there. Yes. You have to say, okay, clock is moving like this, then let's flip the plane, it will be going like that. Yeah. Okay? So it means that the current, there is induced of current without having a battery. Okay? So it means if you have a current, we have the electricity. So then it means that the magnetic field, we know that also if a magnet we push inside the coil, then induce the current. Also that induced current will produce another magnetic field. It means that what is the direction of that induced magnetic field by that current? The direction will be going how? In which direction? It will be opposite. It will be moving like that. Okay? So, then next, we are going to see how also, if also I have that coil plate, that is biomagnets, surf nav, then magnetic field lines. So then, when then I pull away that biomagnet, also we will be having induced current but which will move anti-clockwise. Okay? Then the induced magnetic field will be going opposite. It means that the induced magnetic field will be moving downward. Okay? So that is the overview of the demonstration. So then we are going to make demonstration of moving a bar magnet in and out of the coil by using FET simulation. So then what we are going to see, remember, how can we generate electricity without a battery? Okay? So that is the bar magnet which has nav and stuff, okay? Then that is the coil, okay? And that is here the light bulb. Then if I move that bar magnet, it will produce induced current. Okay? It will not depend that if I move inside, that is the first case. Okay? As we saw it here, also there will be induced current but clockwise. But it will produce also current. And even when I pull that bar magnet away, also it will induce current, but clockwise. But we don't take into consideration the direction of current to be clockwise or anti-clockwise. What matters is about having the electricity using the bar magnet. So, from here, then I want you to try to formulate what is the topic of the lesson today. According to the demonstration we got, conducting and even the demonstration of moving in and out of the coil. What is the topic? I want you to formulate, to try, to brainstorm. Not in our book. Okay, brainstorm. Thank you. Okay, perfect. Okay, how can we award her? Okay? Okay, thank you. Today's of the lesson. So today's lesson is about the Faraday's law and the Lenz's law and the electric field of a practical capacitor. Okay, so before continuing, the remark we have to keep in mind is that the currents wants to oppose the change in the magnetic field, as stated in the Lenz's law. Okay, because the formula, you know it, the Faraday's law, we have electromotive force which is equal to the negative times the number of the turns. It's about how that coil, the number of the turns we have here, then rate of the flux flux is the rate of the change of magnetic field with respect to the time. So this negative comes because the current opposes the change in the magnetic field.
Yes.
Okay? Thank you. Let's call upon next member to continue.
Thank you. Also, by name of the introduce we'll be there number 22301564. So I'm going to continue with the change of the speeds. As you see the change of speed, we are going to deal with this formula of my colleagues have been taught that electromotive force is equal to negative N change in flux. So how change in flux is going to be affected electromotive force? As you increase the speeds, and the change of flux will be increased in high situation. As it goes low, even this one going slow. So in order to understand, let's try and attempt a simulation for better understanding. We are going to, this is a wire with a magnet for south and north, and this is a ring or wire. This is a water, source of water, and this is an above, this is a wire. So we're going to increase this speed of water, and we're going to observe affection of this light if going down or turn off. So firstly, let's start with increasing the low speed of water. So this is a low speed of water. As you see, the bulb is going to speed the little light. As the little light, when we increase this speed of water, as we increase the flux, light can become lighter than this one. So when we increase the speed of water, as you observe, when we're increasing of speed of water, and as that progression to increase this flux also light will be above. As we are integrating this formula, electromotive force of number of turns and change in flux. So I think this is an assertion of to observe where electromotive force is all related to the change of the flux. As you see, when we reduce this speed of water, also the light can be reduced until it comes off.
No. We are going to proceed on our session. We are proceeding to the electric field of a plate capacitor. Also, we are going to use Faraday's law in order to see how the magnetic field are related to electric field. Here we have the formula. This formula means that when we try to change magnetic field, we create an electric field. Here, in real, you cannot see how the change occurs. In real reality, we can see how this change can do occur. That is why in this lesson we are going to see how we can see this change in using an instrument which is called AI, augmentation in reality. You see, you can see how can you change the magnetic field, can change also the electric field. So you can use this in AR, augmentation reality, in order to view how this concept is constructed using AR. That is this image. You can draw how this change occurs using a 2-dimension. This is a 2-dimension view. When you try to use 3-dimension, this is the view. When we use AR, augmentation reality, there is all overview of how electric and magnetic field occurs when you're wearing this instrument in order to see what the change of magnetic field can also produce electric field.
We are going to proceed with challenge questions and guiding questions to follow when you are dealing with this challenge question. Challenge question is, we say that how can we design a capacitor-based system in which a changing electric field produces observable electromagnetic effect? Can Maxwell's question explain this effect? This is the question, and this is the steps to follow. Let's start with step 1. Step 1 says that do not jump 2 formulas immediately. It means that firstly, you are going to know how this capacitor is changing, but without using formulas. Step 2. Use virtual or AR visualization vary one parameter at a time. It means that I'm going to use virtual or AR visualization. I think you know AR visualization. Yeah. Step 3. Which Maxwell equations connect a changing magnetic field to an electric field? You are now going to know which Maxwell equation connect changing magnetic field to electric field. Step 4. Predict what would happen if the capacitor were connected to an AC source instead of DC. You know AC source? Do you know AC source?
Yes.
Yeah, let's proceed. Step 5. Explain how your understanding of capacitor has changed. I know if we pass through step 1, step 2, step 3, step 4, you will reach to step 5. You will be able to explain how a capacitor changes from charged storage device to electromagnetic system and expected learning outcome. After this CBA challenge, students will be able to realize that electrodynamics is not about isolated laws. It means that electrodynamics, it is not separate laws. It is not isolated laws. But it means that physics laws work together, and it is about changing the field directly to produce real physical effects. It means that if we change magnetic field with time, we want electric field. This is the meaning of these words. If we change magnetic field with time, we get electric field which will produce your physical effect.
And here we are going to do this so that we can know whether we have understood what we have been taught. Take a sheet of paper and do this. Explain Lenz's law using one real-life example.
Have you finished?
also searched about learning strategies of electrodynamics. So here we are going to look at learning strategies that we can use so that we can learn more or getting more information about electrodynamics. First learning strategy is elaborative encoding. Elaborative encoding purposefully searches for knowledge connection between thought units to create a repetition of retrieval tips in the memory. Here, for example, we can know the differential form of Maxwell equation. So here, when we are in elaborative encoding, we can base on the differential form of Maxwell equation, and we can also derive its integral form. Learning strategy 2 is retrieval practice. Here is where we can just retrieve the memories in order to strengthen and increase content familiarity than study. For instance, we know that electrodynamics has many formulas. So instead of restudying, you can just sit and take a sheet of paper and try to write what you understand. So when you get stuck, it's where you will just look in the book or in the slides. This is more applicable so that you can just retrieve memory and you strengthen what you have studied for a long time. The learning strategy number 3 is self-explanation. Self-explanation is to explain the step in a worked example in order to learn how to solve problems. Here you can look on worked examples, the steps they used, so that you can base on those to solve many problems, including or looking similar to what you have solved. Learning strategy number 4, utilize online resources. Personalized learning can be supported by online courses and video lectures from institutions. Here you can just go to search or to learn from other e-learning platforms. As we know, we used to see other resources like those other e-learning platforms, MIT Open Courses, and other global open education institutions like Khan Academy, Arson Free Learning, and Udemy. Here we can also include YouTube. As we know, when you get stuck, you always go on the online to search other resources that can give you useful information. Learning strategy number 5, which is the last one, it's about visualizing the physics. Here, as we know, physics has the abstract contents. So here we can use the diagrams, software tools such as phase simulations. Here is where you can understand more about the physics, because you will just visualize the context and try to match it with the real life. Thank you. This is the end of our lessons.